Professor, School of Mathematical Science and Statistics, University of Hyderabad. I am well assured that Dr. Chintamani sir lecture will be path-breaking for the students and teachers. You will definitely enjoy this lecture, and the chairperson of this session, well-known academician, my guide, Dr. V.C. Borkar sir, Associate Professor, Departments of Mathematics and Statistics, Yeshwant Mahavidyalaya, Nanded, also deserve the words of thanks for his motivating presence. Thank you very much, sir. Now I request to Dr. Borkar sir, please start this session.
Good evening to all of you. First of all, we'll put tribute to our Lata Mangeshkar, well-known, म्हणजे आपण जसं म्हणू की आपल्या भारताची जी कोकिळा म्हणून, भारतीय कोकिळा म्हणून जिला आपण गौरवलं होतं, भारतरत्न लता मंगेशकर यांचं निधन झालेलं आहे. आज आपण त्यांना सर्वात पहिले श्रद्धांजली वाहू, कारण आपण या भारतीय 75 इयरच्या अॅनिव्हर्सरी निमित्त हा प्रोग्राम आपण ऑर्गनाइज करतो आहोत आणि त्याचं पण आपण भान ठेवून आपल्या भारतरत्न लता मंगेशकर यांना आपण आपल्या क्लाससाठी श्रद्धांजली वाहून आपण आपल्या क्लासला सुरुवात करू. फर्स्ट ऑफ ऑल, I will introduce Dr. Mohan Chintamani sir. He is an assistant professor in School of Mathematical Sciences, Hyderabad University, Hyderabad, which is located in Gachibowli. He had the specializations in the area zero-sum problem and combinatorics and combinatorial number theory and cryptography. These areas are specializations for him. He affiliated to School of Mathematical Sciences, Hyderabad University, Hyderabad, and for postdoctoral degree, he is associated to IIT Chennai. He had completed his research work, that is PhD degree, from Harishchandra Institute, Allahabad, and he is also associated to our Pune University, Pune. Just now we'll recognize it as Savitribai Phule University, Pune. He had completed the research project at GST. He organized 2-3 workshops with the help of various organizations in his institute, as well as national workshop on the number theory and a workshop on number theory and cryptography in his department, along with BITS Goa. Also, he had completed several research projects. He participated in various conferences, workshops, national and international conferences. He was invited lectures for so many conferences organized in India. They are national, international, particularly he is invited lectures in combinatorics and number theory in the conference organized in February 2017 in Allahabad. Again, he is invited speaker for research trends in mathematics. That conference was organized in the February 2018, and so many conferences, and he also published so many research papers in well-known journals. He had huge biodata. Not viewing his biodata, we will listen him because he had
no sir, biodata
commands
matter,
on abstract algebra, and he will explain us for our Open University student. Not only his lecture is helpful for Open University student, also for our teachers and new researcher also. He had so many motivating programs. I think he will not remember me, but I will meet him along with the C.R. Rao in his university, and one times we'll meet along with Chavan in Chennai IIT.
I
Mr.
think
Chavan
sir.
was there.
I think, sir.
Okay, so
I
I will
remember.
request him on behalf of the organizer. He will start his today's lectures on abstract algebra. Welcome, sir.
Yeah.
And you will take complete 1 hour and you will explain your whole details to our students,
Yes,
so
sir.
that they will motivate not only for a set net, for research also.
Yeah.
Thank you,
Yeah.
sir. Once again.
Yeah. Thank you very much, Chavan sir, for inviting me for this, giving a lecture, and of course, Professor V.C. Borkar sir, for giving us such a long and not necessarily introduction. But anyway, I'm very much thankful to you, all of you, sir, and in fact, all the team who is organizing this beautiful series of lectures. I wanted to be part of this series also, wanted to listen some of the lectures, but due to some medical reasons at my home, I could not. But anyway, I will see at some time recordings. Okay, by the way, I understand that majority are the MSc students, right, sir?
Yes, sir. Yes, sir.
Yeah.
Yes, sir.
Okay, so with an apology to the experts in the area and the senior persons who are in the audience, I will ask them to excuse me, as I am going to concentrate on the very basic topics, especially the Cellos theorems. I would like to introduce and possibly discuss proofs also, so that of course, talking in front of your MSc student is actually a difficult task, right? It is always a task, especially when we are online. Had it been offline class, it is a different story, but online is again very difficult. But this is the current situation, right? We all are going through. So let me cut short and tell all of you that usually I speak very fast. I'm not saying loudly, but I speak very fast. That somehow is natural with me. If at any point of the class, if anyone has any doubt or does not understand what I speak, I will be very happy to be interrupted. So I will ask anyone who has a doubt or could not understand anything or any question, any doubt, please stop me and interrupt me. I will be happy. Okay, so let me switch on this, cameras that are not necessary. I hope I am audible very clearly. Let me come to the notes. So I will share my screen. Just a minute. Yeah, is the screen now visible to all of you?
Yes, sir.
Yeah, thank you. So I'll take some few minutes, using my not that good handwriting, but I want to introduce, and then I will go to the notes where I can rush to the proofs and discuss. I have chosen the topic of today's discussion as Cellos Theorems. As I think some of you possibly know it, there are plenty of Cellos Theorems, but in algebra there are 3 main theorems as such, which lies in kind of advanced group theory course, and usually any postgraduate student should know about them. Proofs possibly one may skip at the beginning, but yes, the applications and the importance is something that no one should miss. So my aim is to somehow try to give some intuition behind it and then go for the proofs and of course applications. So I don't know whether this was covered in the previous classes, something known as class equation of a group. Suppose we have, let me say that we are always working on a finite group. For today's discussion, we are discussing anything only about finite groups. Okay, and group could be abelian or not, that's a different question. So if you recall that what was a class equation for a group was, we had an equivalence relation on G known as conjugation. So what it says that if I have two elements x and y from the group G, we say that x is a conjugate of y, or you like in this fashion, x is related to y if and only if one of them, say y, is of this type, zx, z inverse, for some z in G. So if the two elements x and y are of this relation or of this form, we say that they are conjugates of each other. And it is a straightforward exercise or routine remark that this is an equivalence relation on the set G. And therefore, we like to ask what are the equivalence classes. For example, once we have an equivalence relation, we always ask what is an equivalence class looks like, because the set of all equivalence classes are going to give you the partition of the whole group, or the set on which you are thinking of the relation. In this case, the group G. So what is it? It is simply all those elements which are related to this X, or to say that collection of all the conjugates of X. This is a set, and we call this set as the conjugacy class of the element X, right? And as I said, the set G gets partitioned into the parts where each part is actually this equivalence class. So if I take some element, say x1, and look at this equivalence class, it may cover some number of elements. Then one can go to some other element, say x2, which is not covered by the first class of x1. And then likewise, if you go, you'll get the partition of whole group Z as a set, right? Disjoint partition, that's what it means by. And class equation is nothing but simple fact that the number of elements in the group G now can be taken as the number of elements in the individual classes, because all of so there could be some number, let us say R. So I take disjoint classes of elements from G and just sum them up, because they form a partition of G. This is very straightforward identity, right? Number of elements is nothing but the sum of number of elements in each of the parts. And that is very beautiful fact, came out of an equivalence relation on G, a particular relation, namely conjugation, and this is known as class equation. And I hope when you do the course on algebra or say group theory, this is the first point where you see plenty of applications. And in fact, as Sarah was pointing me out, which is common thing that many of you will go for the NET, SET exams or many other, GATE exam, for example. The class equation is the beginning thing. There will be some questions, or at least in interviews, people like to ask, experts test us by, twisting the class equation and asking some question onto it. So this is one of them, and class equation has plenty of outcomes. It has so many applications. But what I want is that just to introduce you towards Cellos theorem. So for example, if you note that if some element I chose happens to be from the center of the group, so this is known as the center of the group. That means all the elements of the group which commutes with every else element of the group. That's what we call as the center of the group. And if I take such an element, then it is very clear that the conjugacy class of such an element is just singleton set, because that commutes with everything, and the expression for any z is just y equal to x, because the element x is commuting with everyone by our assumption. So the classes are very trivial, means have only one element, possibly only when the case is that element x is from the center. And if x is not from the center of the group, naturally there are going to be at least two elements in the equivalence class. So in standard format, the class equation is also written like this. The number of elements in the group are nothing but the size of the center plus, you look at the following, the sizes of the conjugacy classes, where I am taking the sum is over each equivalence class of elements not in the center, because in the center we know the size is 1, so I can just take 1 plus 1 plus 1 plus 1 for as many elements are there in the center, and that's the contribution here. And rest I do not know, I just put as it is some of the sizes of the conjugacy classes, where the star indicates that it is running over non-central elements. Okay, this is very standard format. And the small observation, or let me write a remark without proving much. There is a very nice thing that we can tell about the size of equivalence class under the condition of conjugacy is nothing but the index of its centralizer. So let me quickly say that the index of the centralizer. So centralizer means those elements which commutes with it. Yeah. Centralizer of an element is nothing but collection of elements which commutes with that particular X, and that is a subgroup of G, and index of that subgroup is exactly same as the cardinality of the equivalence class. One can give bijective map between the conjugacy class elements and the set of left cosets, let me say, for example, of the centralizer. And therefore, this each term here can be replaced by the index as well. Order of G now becomes the center size plus the index of centralizer of X. And again, I put a star here because summation is running over for every element X which is not in the center, and we take one element for each equivalence class. And this is actually the most general and accepted format of the class equation. So it has plenty of applications, as I said. Right? For example, if G is abelian, there is nothing much the class equation gives you. Once G is abelian, every class has size 1, and therefore the right hand side reads it as 1 plus 1 plus 1 only. So G is abelian group. Then the class equation gives you nothing, because I just add 1 plus 1 plus 1 like that, and that is exactly equal to the mod G. It gives you no information as such if G is abelian. But if G is not abelian, it does give you plenty of informations, and I like to quote only one because this is not our primary goal for today. So for example, it says that if G is a P group, that means group of prime power order, then its center cannot be trivial. So its center is non-trivial, where I here indicate the identity of the group. Okay, and also in particular, if order of G is P square only, then using this, that center is non-trivial, we can always show that G is abelian always. Okay, one of the very standard corollary or application of class equation is something like this, which is not that hard, but yes, once we sit it down, I hope all of us can get it. So there is one more topic before I want to embark upon Cellulose theorem, is the group action. So I hope you recall very shortly what is the definition of group action. We say that G acts on a set X if there exists a mapping from G cross X to X. Let me say that G comma X, I just denoted by G dot X, some mapping such that very natural conditions we expect. We expect that 1 dot x should be x for every x in the set x, where one is identity of the group, and the second is that the action should respect the group operations. So if I take G and H as two group elements, then whether I take HX first and apply G onto it, or take GH, the product of group elements, and then act on X, things should be same. Very simple and very obvious conditions or that we can expect for such a map. And such a map we always call as a group action on X. There are several group actions, and each of the particular examples leads us to plenty of beautiful results in group theory. So the primary goal of whole algebra was at the those days, centuries old, let me say, that given a group, abstract group, one likes to understand it. One likes to know the structure of group. One likes to ask the questions about like how many elements of particular order are there in group G, how many subgroups G has, and so on and so forth. So what it turns out to be that if we choose a nice set X and let us say G act on X in different ways, so the action of G on certain set of X determines many things about G itself. So this is how we say in Marathi that anyway, I should say that the way people act on the other thing tells a lot about themselves, right? And that turns out to be very, very true in the group action. In fact, we will see that the Cellos theorem is one of such a incidence of a particular group action. So in this context, let me want to recall this is what I need in the Cellos theorems: orbit and the stabilizer in a group action. So if I say that G acts on X and let an element X from the set X, so I want to say what I mean by G orbit of X. So as the word says, it is nothing but let all the elements of G acts on X and collect the images. That's what we call it as orbit. So in other term, compute G dot X as you run through the group. And that's clearly a subset of X. And the stabilizer is something, as word says, those group elements which does nothing to the element X. The action of this small g on X is nothing. It just keeps X intact. So we call those as stabilizer. And it's a small observation that this is actually a subgroup of G. And that one was a subset of X. For example, let me just give some examples before I run through. Maybe I can give this simple example like this. For any group G, I take the set X as G itself, and we have the action of G acts on the set X, which is G itself as a set, by conjugation. So what is the mapping that I defined? G dot X, I defined it as GX G inverse. Okay, we can check this is a natural, I mean, not natural, but one of the beautiful action of G on the set G itself. And this is exactly leads us to what we have just seen as a class equation. So if I look at orbits, what are the orbits in this action? This is nothing but conjugacy classes. Conjugacy class of X that we have just seen above, and I think I have given this as a notation. Okay. Stabilizers are subgroups, as the word says. Stabilizer of X under this action is nothing but, let me say in the word, centralizer of the particular elements. So a particular action, namely the conjugation on G, had already occurred to us, namely in the class equation, right? That's one of the action that is very much handy in many contexts, not just in the case of group actions. Similarly, if I take the one more action that we need in the Cellos theorems, is that G acts on G by left multiplication. Means what? I just say G dot X is defined as GX, where this dot is a group operation. And this is the operation of action that I'm defining. Simply take the operation of G as it is. Okay. And you can, try to find out what's orbit and how does they look. One more example of group action that I like to give is the G acting on set of all the left cosets of some subgroup. I fix a subgroup, let me call it as this, set of all left cosets. I take H to be a subgroup, some subgroup, and look at the set X as set of all left cosets. I just take all left cosets and let G act on it by very natural way. So G cross X to X, the action that we are giving is G dot or G comma XH is a coset. I define it to be GXH. Right? I just change the coset representative. And you check that this is also a group action. And let me write what are the orbits looks like. So what is the orbit of XH in this case? So the definition says that look at GXH as you run through the group, right? And I like to put here a question mark for one to think that how this set look like. Can you recognize this set? Stabilizer similarly of an element which is a coset in this case. How does it look like? I look all to those group elements such that the action of let me just a second, sir. I'm talking about the left multiplication. Okay, so that's not a big deal. I just want those G such that GXH is same as XH. The coset should be intact upon action. Okay, this statement can be modified, and you can look it like that. This is same as X inverse GXH must be same as H. Right? So here X is fixed. Right? And the question is that can you recognize this set? How does it look like? Little computation or let us say observation says that this is exactly the set like this, X, H, X inverse. And in our term, we call this as the conjugate subgroup. Right? H was given subgroup and X, H, X inverse is a conjugate of the subgroup H by the element X. So stabilizer turns out to be conjugate of H itself, conjugate subgroup. Orbit is very natural. One can look at what it looks like. And again, there are few more group actions that we like to see throughout the course. But in all those things, there is a very small result which is very handy in many applications, which is known as the orbit stabilizer relation. What it simply says that the size of any orbit, the number of elements in the orbit is just same as the index of the stabilizer subgroup. Right? Again, as we have seen in the conjugacy class or conjugacy action, that number of elements in the conjugacy class is the index of the centralizer, and observe that centralizer is nothing but the stabilizer in this action. So index of stabilizer is what says the size of the orbit, and that in fact is generally true, not about just the action, namely conjugation. It is true for general group action. So this is again, let me not go into it because it is really straightforward. By producing a bijective map between the two sets, one can show this. But remember that this is actually what we have seen it as a class equation. Point to note is that this was a class equation really. I mean, this leads to class equation, not just as it is a class equation, because once we know the size of the groups, one can just write the number of elements in the set X as the cardinalities of orbits. if I say that, let us say x1, x2, and so on, say xr, are the R elements whose orbits, if I take, they cover up whole the set X, right? And this what was really the class equation in particular. Okay, so far so good. I was just rushing through because I finally wanted to turn to the Cellulose Theorem. If you have not seen this before, you can ask me, of course, but you have to bear with me as well for some time. There are plenty of applications, as I said before, and in fact, as Sir also told Borkar sir, that these are the topics which are very frequently being asked in net set exams, at least for those who are, aiming the net set exams. This is something that they cannot avoid as long as you are in a pure mathematics, at least. Okay, there will be definitely some questions, may not be straightforward, but some twisted questions on these topics. So one needs to understand concepts very well, and then application is the different part. But unless you understand the application concept itself, the applying it becomes a little awkward. Okay, so just for your record, I want to mention some of the applications of group actions, very well known and celebrated ones. One of them was very famous, and due to the mathematician Calais, that we know in algebra as Calais' theorem, that every group G is actually a permutation group for some set. That was one of the application of classical application of group action. There is one more that you might not have heard before, that Bernstein's counting lemma or counting principle. When we have, for example, certain objects and there are certain colorings of the vertices or beads, as you call, are given, and we like to know that how many distinguishable ways are there to build such a configuration. Counting set is not straightforward in general that way, but it was Bernstein's instinct who applied the group action to give exact counting of distinguishable objects with possible colorings. And that's now known as Bernstein's counting principle or counting lemma. I'm not going to do that also. And one of the prominent application of group action is the Cellulose Theorem. So structure of subgroups is what the main topic of Cellulose Theorem is. How the subgroups of a given group are, or what properties or what things we can say about subgroups of G, if G is some given group. For example, you definitely might have known this theorem due to Lagrange's theorem, that if H is any subgroup of G, then the order of H is always a factor of order of G, right? It's very trivial. And again, I want to repeat, all these group actions, or so-called in particular class equation, was we have some equivalence relation and get the partition given set G. So G get partition into several parts, and summing the parts gives you the cardinality of the full G. That was the basic underlying simple phenomena, right? And the Lagrange's theorem is also one of such phenomena. Given a subgroup H, we just give the set G as partition into the set of left cosets. They get partition, and therefore order of G becomes sum of the parts. But in particular, this case of Lagrange, these particular parts are of same size, and this is how we lead to the theorem due to Lagrange, saying that the order of G is a multiple of order of the group, no matter what group is. Okay, as long as it is finite group, this makes sense. Okay, the group, I hope all of you have seen and this thing. One likes to ask the question is about the converse. What about the converse? That if I have given a group G and say some divisor of that group order, we like to ask the question that can you answer affirmatively the existence of certain subgroup with that order, right? And answer is in general no to this question. Is anyone having some doubt or want to interrupt? By the way, students, as I told, this is naturally, I just go fast. Please stop me if you are having any doubt or you want further clarification. Okay. I took almost 15-20 minutes just to motivate or give the how the Cellos theorem has inline come across. The actual content will begin little now. So converse of Languages theorem is not true in general, and there is plenty of classical examples, but one is enough to say that this is not true in general. Is the following: you take the group to be A4, right? Group of alternating permutations on 4 letters. You know that size of this group is 12, and 6, for example, is the divisor of this order. But A4 has no subgroup of order 6, right? This is classical, and in fact, it was my days of net set exams where this question was very commonly asked. Okay, give an example of a group which does not have subgroup of given order. For example, this was 6 divides 12, and there is no subgroup of order 12. Okay, there are plenty of proofs of this fact, but many of them converge on a single fact that if there is a subgroup of 6 order in A4, then being index 2, it is normal, and hence A4 will contain all the 3 cycles. All the 3 cycles of length 3 will be inside that subgroup H, but then subgroup H has size 6, and A4 has 8 number of 3 cycles, and this simple counting will lead you to say that such a subgroup is not possible to exist. Okay, but anyway, once we have one example, there are little more examples one can ask, and then as a mathematician we like to ask, okay, fine, this is not true in general, but where is this true? Where is the converse true? We ask that in what part the converse is true, or more precisely, one may ask that in what context or in what level of context the converse is true. For example, one may wonder that, okay, because 6 is not a prime number, though it is the divisor of order of the G, it is not a prime, and possibly a divisor not being a prime was a hurdle for converse of Languages theorem. And that turns out to be not really the case. There are examples of groups where divisors are not prime and still there is existence of such a group. And Cello was the first mathematician who kind of tried to give the converse possibly to the most general form. And here we begin with actual content, the Cellos theorem. Many of the books that we have seen, or possibly we have seen as references, there are 3 theorems as such: Cellos first theorem, Cellos second, and Cellos third theorem. So let me just come to that notes I want to discuss with you. Just a minute. I am sharing that. Where is the Google Meet? Sorry, this. So I am going to share some notes with you and possibly go through it. And if you have doubt, of course, you can read it and ask me again whenever you have time to read it. So let me come to it. How can I share this? Are you able to see these notes? Sir, can you reply? Someone?
No, sir.
I'm unable to find my Zoom window where to share that. Let me minimize. Yeah, I saw it now. Good. So I want to share this one. Drawboard. Yes, this one. I think is it visible now?
Yes, sir.
Yeah, thank you very much. And sorry for this delay. So there are some handwritten notes. I wanted to I would have been far comfortable, giving you the board lecture, but due to this pandemic, we all are, in some different level. So we have to go through it. So this is what I just talked to you a little while ago. And here are the main three theorems due to Silo in the group theory that have a prominent, important in these applications of group theory, let me say. And again, I repeat for the students' sake, the next set exams certainly contains always some questions in these topics: group action, Cellulose theorems. There are several Cellulose theorems. As I said, we are going to see the three out of it, and their application mainly. Okay, so the first theorem is says that if I have a prime number p, and let us say that a power of it divides the order of group, p power L is a factor of order of G. If that is the case, then the converse of Languages theorem is true, is what first Cellulose theorem says. It says that no matter what prime power you have, as long as that prime power is a factor of G, order of G, then there is a subgroup of that order. That's what the first Cellulose theorem says. The beautiful and but most applicable is the second one, which says that you write the order of the group as this: p to the power alpha times n, where alpha is the largest power of p dividing order of group. Okay, and you take H to be any subgroup with this condition that its order is some power of p power beta, let us say. Okay, if I take a subgroup of G having any prime power p power beta, of course beta will be between 1 and alpha only, because p alpha is the largest power of p dividing or sitting inside mod G. Then the second theorem says that it always sit inside a subgroup H tilde of G, where H tilde has order p to the power alpha. The subgroups of largest prime power order possible are known as Silo p subgroups. And the second theorem vaguely says that every subgroup with prime power order is a subgroup of some Silo p subgroup. So it is chain, right? If I take a subgroup of order p square, then I can find a subgroup of order p cube where p square sits inside p cube, and so on and so forth. And I can go till the last level, p to the power alpha. So everything is inside some Silo p subgroup. That's what the second theorem says. So there is a chain of subgroups possible. And third one is actually the counting thing, that how many there are how many number of Silo p subgroups, for example. And third says that the number of Silo p subgroups, I repeat, the Silo p subgroup is a group of order p to the power alpha, the maximum prime power. And number of such Silo p subgroups gives you a lot of insight into the group structure, especially the group is simple or not. And for a finite order, the classification of groups is also given by knowing how many Silo p subgroups are there. The knowledge of number of Silo p subgroups highlights certain important facts about the group itself. And the third theorem is exactly talking about that number, that how many Silo p subgroups are there in general. It says that the number is really 1 mod p. So the number of Silo p subgroups, if I say np is number of Silo p subgroup, it is of this type, 1 plus some k times p. That's what the third theorem of Silo says. The number of Silo p subgroups are always 1 plus k times p in number. So k could be 0 or 1 or 2 or 3 and so on and so forth. So for example, there is at least 1, and then there is 1 plus p next possible, or 1 plus 2 times p, and so on and so forth. So the number of Silo p subgroup is always of this type, 1 modulo p. And also it is also a divisor of the order of G. So this number np, the number of Silo p subgroup, is also the factor of the order of the group. Okay, just a minute, let me adjust this one. Yeah. So this combinatorial information is actually the heart of whole application of Cellulose theorem. This NP, for example, suppose NP is 1. The first theorem, recall that if you understand, it says that if I put L equal to alpha here, then there is at least one subgroup of order p to the power alpha. And therefore, that is a Cellulose P subgroup by definition. And what it says that if there is only one such subgroup, Cellulose P subgroup, the second theorem simply says that it has to be normal. Right? Because we'll see that in the application, if the proof is really constructive proof, the second and third theorem have the constructive proof. Okay, the first theorem has the proof that we are going to outline is actually inductive proof, but the second and third theorem are really constructive. One can, have the proof, run through it, and you will get the output that we expect. So in particular, we will see that if the number of Cellulose P subgroup is only 1, then the subgroup is always normal. And I hope in the very first few classes on group theory, one always asks that importance of having a normal subgroup. Just a subgroup is not enough, but if we have a normal subgroup, then we can factor the group out. So given the group G may be large enough, we can factor it out through a normal subgroup, and then we can kind of form smaller groups. And there are so many results in the literature that says that if you know the partition of the group into the nice parts, the parts being very nice, so that the parts itself are groups, then one can fetch the information of G itself. For example, if you know the Cauchy's theorem about a certain order element exists in the group G, that is one of the classical example of choosing a very nice normal subgroup. Therefore, asking existence of a normal subgroup is a good question, and people will be happy if you know that certain group is normal or not, because straight away you can form a new group, namely quotient group or the factorial group, as some books like to call it as. The Cellulose theorem says that if the number of Cellulose P subgroup is only 1 for certain number p, certain prime number p, then that subgroup will always be normal, and therefore it is also one of the good achievement. Okay, so proof again, as I said, I will see it. We can go through the proof. There's no, it is in almost every textbook and fairly standard also. But there are certain books like Dummit and Foot, for example. If you would like to refer, you may get different proofs of the Cellulose theorems, or if you are famous with Galilean or say abstract algebra by Fraley, you may have different. They have different flavors, the authors, and therefore they would like to present a different proof of the same theorems, because they are so classical theorems and they are so widely applicable. There is no surprise that there are plenty of proofs. There are not just one proof which was given by Cellulose. There are many modern proofs coming up. So I will be happy if you just understand at least the statements of the theorems and try to apply it. So for example, before going to the proofs, which are anyway I have written it for purpose of discussion, I can run through it, but let me just go through the application part. Here are some illustrations that I wanted to discuss at the end of the class, but let me before my time runs out, I want to illustrate and then go back to proofs. So for example, suppose group is given to be of order 15. Say some group is given and say its order is 15 given only, no other information. We do not know what group operation is given, right? When we have some set G, the same set G may have different group operations, and that may make G into group. But suppose we only have the thing that G has 15 elements, that's it. What can you say about such a group? And the Cellulose theory can be applied to say a few things about it. For example, you write 15 as 3 into 5, 3 and 5 are primes, and talk about Cellulose theorems and Cellulose 5 theorems. Sorry, subgroups. For example, P equal to 3, if I put, and say P equal to 5, you look at how many Cellulose 5 subgroups are there. The theorem says that one of the theorems says that it is 1 modulo 5, so it is either 1, or 1 plus 5, which is 6, or plus 5, which is 11, and so on, suppose, right? The one of the conditions says it is 1 modulo 5. So it can have the choices 1, 6, 11, and so on and so forth. But the second conclusion was it is a factor of the order of the group as well. So n5 is a factor of 15. And then you can combine this, that among this list of possible number of Cello 5 subgroups, which one satisfies the condition that it is a factor of 15. And then you will check that n5 equal to 1 is the only choice. And hence, there is only one Cello 5 subgroup, and therefore it has to be normal, as we have just pointed out. Okay. In fact, little further calculation, not much, but little further, we can show that in fact the group must be acyclic, and therefore it is isomorphic to Z15, the group of integers modulo 15. So every group of order 15 is going to be cyclic always, not just abelian, it is cyclic. And the Cellos theorems plays a vital role to complete this reasoning. I repeat again, the knowledge of Cellos theorems, namely Cello 3 subgroups and Cello 5 subgroups in this case, plays a role. Luckily, each of them have only one number, and therefore they become normal. And then small further calculation or say manipulation will tell you that such a group will always be cyclic. But as the number grows, or for example, if there is more power of 3 than just 3 power 1, then still we can work out through the Cellos theory, coupled with some other basic theorems that we know already from the previous discussions. If you have class on algebras, we can still go to classifying the groups. For example, it is in general true that if I take the order of group to be p times q, with p and q say prime numbers, distinct prime numbers, and suppose that the small prime p does not divide q minus 1. That means if p is the smaller prime and q is the larger one, then I want the condition to be that p does not divide q minus 1. Then the group is again cyclic, and exactly the reasoning as we gave before really works. Not just for 15, we can say it for p into q times. But the condition is something important, that is p should not divide q minus 1. Of course, if p divides q minus 1, there is again further calculation and further modification of the Cellos theory. Okay, a clever manipulation, and we can even classify that group as well. But we have only 60 minutes to discuss, and I think you can go to the notes, of course, and there are plenty of classical books like Dummett and Foote, for example, or the Freile book, which has several exercises and good explanation. You spend time, I'm sure that you can get plenty of applications of this kind of Cellos theory. But as I said, these are the common questions, not so straightforwardly as I wrote here, but in a different form. They are generally being asked in many competitive exams, including SET and NET, and possibly GATE as well. Okay, this was about illustration. If someone has any doubt or any comment, I would like to ask you. If you have any question or doubt, please feel free to ask. We are going to see the proofs of Cellos theorem, which are basically applications of group action. Choose a particular group, let it act on particular set X, and that particular action is going to lead us to the theory. Of course, not just group action, we need some further observations as well. So among the students, I like to ask if you have any doubt or any more clarification you will you want. Of course, I feel sorry to ask you doubts if you have, because hardly we have 45 or so minutes discussed, and again I'm asking you if you have any doubt. Definitely we need some time to digest, understand, and go through it. Only then one can think of some questions and come up with good discussion. But still, at least for those students who have seen this before, they can understand it in more details and pose me some questions or discussion if you want. By the way, I am also Marathi, so as I understand, many of you are Marathi people. So I, with excuse to the people who are not non-Marathis, you can ask in Marathi questions in Marathi also. I will be glad to help you out.
बुक्सची नावं ग्रुपवर टाकाल का सर?
हो, नक्की टाकेन, जरूर. रेफरन्स मी देईल तुम्हाला, नक्कीच देईल. Borkar sir, I have some 10-15 minutes more.
So you can take 5 minutes also,
Okay, fine, sir.
so that you should discuss with the student and all audience other than students.
Yes,
What
yes.
If they have doubts, they
Right.
may ask.
Yes. I think you have class also after this, right? One more class is there. I mean, lecture.
Yeah.
Yeah. So I like to stick to time. Okay, I will take 5-10 minutes more, not more than that. As I said to you, all of you students, see, this is such, of course, though it's advanced part of group theory course, but still it is a, not so advanced. It is very classical, and as I said, it is quite old topic. But though it is very relevant in the nowadays also, any research, if I talk about on the groups or say finite groups is going on, these theorems are just being used right and left. So whenever you think of this is a century-old result or so, you should not mislead yourself. They are of practical importance right now as well. Whenever you take a research level topic on group, let us say, these theorems are being used even without reference many times. They are of so much importance. Okay, and as I said, as a student of MSc or graduate student, nevertheless, definitely you are going to see some questions on these topics, in interviews at least, and in fact in some competitive exams as well. Proofs of these theorems, as I said, the first theorem is not that at all hard to prove. It's a routine induction method. Let me just come to the page without going to details. The first theorem is really nice. You just choose a nice normal subgroup, factor out your given group G, and apply it to the factor group, quotient group, and you pull it back to the group G itself. This is the common phenomena which is very successful in many contexts, and hence so is in this first theorem as well. We choose very nice subgroup and apply the induction. This is how the first theorem is being proved. Once you go through it, I think possibly no one can miss it. Something really required is in the second and third theorems proof, where let me use maybe this blank area. I hope I have somewhere a blank area. No, let me come here itself. So idea is really nice. So let G act on the set of left cosets. So let me say X, where there are so many sets. At one place we take all the left cosets of certain particular subgroup H. Sometimes we may take X to be Cello subgroups only. We take set of all the Cello P subgroups. So each Cello P subgroup is a single element of the X, and we let cleverly group G act on that set of all Cello subgroups. And then something comes out of it. We play with some combinatorial equations, and the second theorem or part of second theorem will be result out of it. And many times we restrict the group action. Restrict the group action. Instead of G, you take some part of the G and again think of the same group action. That also has led or played a role in the second and third theorems proof. As I said, first proof is very straightforward. Second and third requires a little bit manipulation of different group actions. Same set is being acted upon by two different groups, and other way around. Same group acts on two different sets. So this is how I said that group actions, are, being used, and Cellulose theorem is one of the beautiful outcome of group action. Maybe I think I would like to stop, as going to the proof is, one can always go through it by their choice. I can share these notes with you, students. And if anyone has any doubt, question, they can anyway contact me at any point. Borkar sir, I think I can stop it here, if you don't mind.
Sir, thank you for your fruitful lectures. So
There is no point of giving the proof, unless we have sufficient time. And I would be very glad or happy also if students get motivated towards why one should think of Cellulose subgroups and how it has been developed overall. Because one can go to the books and see the proof at any point whenever they want. But in a class or in a seminar, let us say, one should be really happy if one gets motivated towards it. And anyway, what I have taught is from some books. It's not that out of the sky somebody is teaching. It is in almost some book or the other book. So students, I hope you at least get the idea or glimpse of what is Cellos theorem and how it is being used, maybe in the very minimalistic way. Okay, sir.
Thank you.
Over to you.
Thank you, sir. Once again, student, it's a very used topic from abstract algebra. Not only used, but it is also useful for set, NET, examinations and research in algebra. So many concepts of Cellos theorems are required for research in algebra. So that's why in his introductory lecture, Professor Mohan Chintamani sir nicely elaborated few concepts regarding to the abelian groups, the applications of Cellos theorem, Lagrange's theorem, and from basic aspect to the Cellos theorem. So these Cellos theorems are very useful for your future works. Those students who are interested in algebra, they should came across all the concepts. I will request on behalf of you, because so many charts are available in the chat box, that Professor Mohan Chintamani sir will provide you the list of books on abstract algebra, very good books on abstract algebra, which
Yes,
he
sure.
had referred during his study.
Yes,
So
sir.
on behalf of Digambar Bindu Mahavidyalay Bhokar, who organized the 75th Azadi Ka Amrit Mahotsav 1 week national lecture programs for the students, not only for YCM students, for other students and mathematicians. Yeah, so in collaboration with IQSC, Department of IQSC from Bindu College and YCMU University Study Center. So I will thankful to all of you. First of all, I will thank to Professor Mohan Chintamani sir, who had nicely elaborated the concept regarding Cellos theorem, Cellos theorem, and class equations, how they are useful, and he had taken some examples. All of you are just not aware about this. That's why you feel it difficult. But in mathematics, first of all, if you study anything, you feel difficult, but they are very nice concepts, and he had nicely explained for you. So on behalf of organizer, I will thankful to Dr. Mohan Chintamani sir.
Thank you very much, sir.
He had
And
taken.
I also want to put forward to all of you, thank you for listening
sir.
peacefully to me.
So again, I thanks to the principal, Dr. Punjab Chauhan. He had provided nice food for our mathematics community and his team. So with the permission of chair, I will say that the first lecture, it is a 6th lectures will be over. So I will request Dr. Chauhan sir, please forward to next lecture. Thanks one again. You student also, all of the students who are participated, and not only just participated, your participation is actively involved in the lecture. So that's why all of you have credit to put the thanks from the organizer. So I will again thanks to all of you, and request the organizer to please forward for next lecture. Again,
you, sir.
thanks to all of you.
Thank you, sir. Thank you very much. I am very much thankful to Dr. Mohan Chintamani sir, the resource person of today's session, on behalf of our college and departments of mathematics, for accepting our invitation. Dr. Chintamani sir discussed so many things in algebra. Particularly, he shared with students his deep insight into his topics. Definitely, it will be the great help to the students of BSc, MSc, SET, NET examinations. And thank you very much, sir. I am also
Thank you very much,
thankful.
sir.
I am
thank all of
also
you.
thankful to Dr. VC Borkar sir for chairing this session and for all his ready help to the national
अनु
level lecture
अनुष्का,
series.
चल बाहेर थंड
Thank you very
पडायला
much, sir.
आता.
Borkar sir.
तिला
Thank you.
सर्दी होईल. कुठे आहे ती? हा चला. काय ग?
Hello. Jadhav sir.
बोला हॅलो
हाँ स्टार्ट करा था दूसरा सेशन स्टार्ट
करायचं लगेच
ब्रेक द्यायचा का विचारा ना त्यांना काय म्हणतात
हॅलो
हा सर
करायचं लगेच स्टार्ट
हो
करायचं काय
हा लगेच स्टार्ट करून टाकू
ठीक आहे ठीक
हो
हो ओके ओके okay so today's second session is now going to start. Good evening to one and all. Firstly, I warm welcome to the participant and resource person Dr. S.B. Chavan sir. Actually, I am very much thankful to the organizing committee for giving me this opportunity. On the occasion of 75th Azadi Ka Amrit Mahotsav, Department of Mathematics, IQAC and YCMU Study Center of Digambara Bindu ACS College Bhokar organized a 1-week national level lecture series on mathematics. Actually, it is very interesting event organized by the institution. So I congratulate all of them. Now today's resource person is Dr. S.B. Chavan sir will deliver his lecture on the numerical analysis. Friends, numerical analysis is the study of algorithm and it finds various applications in the field of engineering and physical sciences. And in the 21st century, it also finds applications in medical science, life science, social science, and business and arts also. So today's resource person, Dr. S.B. Chavan sir, I request him to start his valuable thought on the numerical analysis. Hello. Sir.
Hello. Oh,
Yes.
I am very much thanks to Dr. Jadhav sir to very nice introduce by me. So I short. Hello. May I audible? Hello.
Yeah, sir. Yeah, you can
Okay.
start. Yeah,
So
sir.
I
You are
start
audible.
I start without much time. Dear student, today we are going to talk about numerical analysis. Numerical analysis and numerical method, both the same things, but name is different. So here I will share my PPT. So numerical analysis, these are the definitions of numerical analysis. In reality, solving a math problem generally involves finding an answer rather than exactly answer. So next one definition is numerical analysis is a study of algorithm that use numerical approximation for the problem of mathematical analysis. Next, a trick that let you get closer and closer to the exact answer is a numerical method or numerical analysis. So numerical method to find the solution of closer to the answer without ever knowing that answer is such an important part of every numerical method is a proof that of work. So what is the these are the definition of numerical analysis, and what is the needs of numerical analysis and applications of numerical analysis in various fields. So first need of the numerical analysis is analytical method may not exist. That means here if we given that the ax square plus bx plus c is equal to 0, this is the quadratic equation. These quadratic equations uses two roots, but we can easily find out these roots. But here this is called as analytical method is exist, but we have to given that if x square plus tan x plus 10 is equal to 0, or if you have to given the fifth degree polynomial, and how to find this roots of these equations by using analytical method exist. Yes, this is the time consuming method, but analytical method may not exist these types of roots. Then we will find out using the numerical methods. Then here we use the numerical method. Next one, second needs is data available does not admit applicability of direct analytical method. So data available does not admit applicability of analytical method. So that means here we use interpolation. We use interpolation. That's why if we have to given some examples, you have to given the population of cities or populations in India in 2001 is 100 crores, and 2015 this one is 120 crores. But interpolation means if we find out the population between these 2 years, this is called as a interpolation. We cannot find out these populations by using average mean. That's why we use the interpolation method. But what is the difference between interpolation method and extrapolations? Extrapolations means if we find out these populations outside by this interval, yani outside the 2001 to 2015, yani we will find out 2000 and 2016, 2017, like this. This is called as a extrapolation. So here one minute please. Yeah. So next one is applications. Usually used in computer science for roots of algorithm. It is also used determine the profit and loss in the company. This numerical analysis or numerical methods is also used to multi-dimensional roots finding and solving the practical technical problems using scientific and mathematical tools, train and traffic signal, weather prediction, build up the algorithm. These are the applications to use the numerical analysis or numerical methods. So next we are going to talk on operators. What is operators? so many operators in the numerical analysis. What is the need of numeric operators in the numerical analysis? Then finite difference calculus. If we have given that input, then algorithm and output. This system, input, algorithm and outputs, that means this is the systems. If you have to given the input 2, 4, then we take the algorithm for addition and we will get the output or results. Therefore 2, 4 is our input, then algorithm is additions, then 2 plus 4 is equal to 6. If we change this algorithm addition to multiplication, we will get the different result. 4 into 2 is equal to 8. Then this process of the operator is used to algorithms. That's why there are many operators: identity operator, shift operator, it is also called as a displacement operator, forward difference operator, backward difference operator, it is also called as a nebula, del, d, pdf. So what is forward difference operator? So here with it, forward difference operator, it is denoted by delta. Okay, so what is the definition of this delta? The definition of this delta f of x is equal to f of x plus h minus f of x, where h is an any interval. यहाँ पे h is a interval है. So again we find out second order second order del square f of x is equal to, we write here del f of x. Therefore del is as it is. Therefore del f of x is equal to f of x plus h minus f of x. There f of x plus h minus f of x. We again operate this operator on the bracket, del f of x plus h minus del f of x. Then again we use, what is the change of this original definition? If here del f of x is equal to f of x plus h minus f of x, yani we add extra h from this. Therefore del f of x plus h is equal to f of x plus h minus f of x plus h. Then we take another one bracket, del f of x is a similar definition of f of x plus h minus f of x. Then we write here f of x plus 2h minus, this is 2 times f of x plus h minus f of x. Sorry, this one is a plus f of x. This is del square f of x. Similarly, we find out del cube f of x. Then we write here again del square in bracket del f of x, and till this process continuous. Then we will see the next operator, backward difference operator, or it is also called as a nebula.
स्टेप समजून सांगा अजून एकदा.
ओके ओके सांगतो, एक मिनिट. Okay, Which one?
Sir.
Okay. Del f of x is equal to, this is the forward difference operator. Del f of x is equal to f of x plus h minus f of x. This is our original definition of forward difference operator. H is any interval. H is any interval. Then we find out del square f of x. This is equal to del in bracket del f of x. This is equal to again del. Then we use del f of x is equal to, this is the above definition, f of x plus h minus f of x. Then use this operator on this bracket. Therefore, del f of x plus h minus del f of x. So we write here again del f of x plus h. Del f of x plus h. F of x plus h minus f of x plus h minus in bracket we here f of x plus h minus f of x. According to definition, we write his del f of x is equal to f of x plus h minus f of x. Then again f of x plus h 2h minus f of x plus h as it is. Then we multiply this minus sign into this bracket. Therefore, f of x plus h minus plus f of x. Then this term is 2 times f of x minus f of x plus h minus f of x plus h. This is equal to 2 times x plus 2h minus 2 times f of x plus h minus plus f of x. This is the second forward difference. Then similarly we find out third forward difference. This is del square in bracket del f of x. Then similarly we find out using the according to definition of forward difference definition. So next one is backward difference. So backward difference operator is denoted by backward difference operator. It is also called as nebula. It is also called as nebula. So what is the definition of backward difference operator? Therefore, backward difference operator f of x is equal to f of x minus f of x minus h. Nebula f of x is equal to f of x minus f of x minus h. So second order nebula f of x is equal to nebula f of x. Then we use the original definition here. Nebula, this bracket nebula means f of x minus f of x minus h. So we operate this operator nebula f of x minus nebula f of x minus h. So we write here nebula f of x is equal to.
Hello.
Yes, sir. Yes, sir.
Hello, sir.
Yes, sir.
All participants are requested to mute their microphones. Or mute them, sir.
Okay. Hello. Hello.
Continue, sir, please.
Okay.
Continue, sir.
So nebula f of x. Nebula f of x is equal to, here we write f of x minus f of x minus h. Again we take bracket f of x minus h minus f of x minus 2h. Then here we write f of x minus, this one is the 2 times, again 2 times f of x minus h, then plus f of x minus 2h. So till this process we will find out this one is the Nebula square, means second order backward difference. Then again we find out del f of x means Nebula cube f of x, and we use again Nebula square in bracket Nebula of f of x, like this. So next operator is the shift operator. Next operator is the shift operator. Third operator is the shift operator. It is denoted by capital E, and it is also called as displacement operator. So student, what is the definition of E of f of x? Therefore, E of f of x is equal to f of x plus h. H is an any interval. Then we again E square f of x is equal to, here we write E of f of x then use E as it is. This E of f of x and f of x plus h according to definition. Then again we operate this E on this f of x plus h. Then we'll write again f of x plus 2h. Then till this process continues here. This one is the second order shift operator. Then we till this process E cube f of x is equal to f of x plus 3h. Again e raised to 4 f of x is equal to f of x plus 4h. Until this process e raised to n f of x is equal to f of x plus nh. F of x plus nh. Similarly we find out the inverse operator. Therefore e raised to minus 1 f of x is equal to f of x minus h. Then e raised to minus 2 f of x is equal to f of x minus 2h. Till this process again continuous, e to the power minus n f of x is equal to f of x minus nh. F of x minus nh. So dear students, these are the three operators: forward difference, backward difference, and shift operator E. Then we use this operator to what is the systems, then use this operator for algorithm for operations on the process of the operators, and we will get the output of the machine. So again here, what is the relationship between these operators? The first relation of these operators, E is equivalent to or equal to 1 plus delta, yani forward difference, or it is also written in delta is equivalent to E minus 1. So according to definition, what is delta f of x? Delta f of x is equal to f of x plus h minus f of x. So delta f of x is equal to f of x. What? 1 minute, please.
Yeah.
So E of f, this is the first relation. Shift operator E is equivalent to 1 plus delta, or delta is equal to E minus 1. Then the definition of forward difference operator, delta f of x is equal to f of x plus h minus f of x. Then again we write delta f of x is equal to f of x plus h, इसका मतलब है so e of f of x is equal to f of x plus h. Yani e of f of x is equal to f of x plus h. We use this relation here. We use this relation f of x plus h, yani e of f of x minus f of x. Then delta f of x is equal to, we take f of x is a common, e minus 1 f of x, then this will get cancelled, therefore delta is equal to e minus 1. And again we write here delta is equal to e minus 1 and e is equal to 1 plus delta. This is the first relation of delta, means forward difference operator delta and shift operator e. Then another one relation is nebula is equal to 1 minus E inverse, or E inverse is equal to 1 minus nebula. So here we write what is the definition of nebula. Nebula f of x is equal to f of x minus f of x minus h. Then again, what is e raised to minus 1 f of x is equal to f of x minus h. Then we replace here nebula f of x is equal to f of x minus e to the power minus 1 f of x. Then we write again nebula f of x is equal to 1 minus e inverse f of x. Then f of x will get cancelled. Then nebula is equal to 1 minus e inverse. Then we write here e inverse is equal to 1 minus nebula. This is second relationship between nebula and e inverse. Then again we use third relation is e nebula is equal to nebula e is equal to forward difference delta. Therefore, we prove this using according to definition e nebula f of x. Then we use here e into nebula of f of x. We operate nebula on the function. Therefore, e as it is. Again, what is nebula of f of x? According to definition, f of x minus f of x minus h. Then this is shift operator e. Then e of f of x minus e of f of x minus h. So we write here e of f of x. What is e of f of x? E of f of x according to definition x plus f of x plus h minus e of f of x minus h. Yani f of x minus h plus h. Then h will get cancelled. Here f of x plus h minus f of x. This is the definition of forward difference operator delta. This is the definition of forward difference operator delta, delta f of x. Therefore, e nebula f of x is equal to delta f of x. Then we will get cancelled. Therefore, e of nebula is equal to delta. Similarly, we prove this. Then again, next relation is number 4. Delta minus nebula is equal to delta into nebula. So we write here delta into nebula f of x is equal to delta in bracket nebula f of x. So delta as it is, what is nebula f of x? According to definition, this one write f of x minus ch. So again we use this delta operator on this function, delta f of x minus delta f of x minus ch. Then according to definition, delta f of x is equal to f of x plus h minus f of x. Then minus in bracket we use again delta f of x minus h, and then we write as f of x minus f of x minus h. So f of x plus h minus f of x minus f of x plus f of x minus h. So we take the common of this minus sign. This is f of x plus h minus f of x as it is. Then we take the minus sign common. Then we again write delta and minus nebula. So next is number 5. The fifth relation is 1 plus delta into 1 minus nebula is equal to 1. So here we write, proof is very simple. 1 plus delta and 1 minus nebula f of x. Then again we write here 1 plus delta outside the bracket, in bracket 1 minus nebula into f of x. Then we again one plus delta as it is, again f of x minus nebula f of x. So 1 plus delta as it is, again f of x minus, what is nebula f of x? Nebula f of x is the definition of f of x minus f of x minus h. So 1 plus delta into f of x minus f of x plus f of x minus h. Then we write minus f of x plus f of x will get cancelled. Then 1 plus delta into f of x minus h. Then we use again f of x minus h plus delta f of x minus h. So here f of x minus h as it is, then we use delta of f of x minus h. That is, we write here f of x minus f of x minus h. This will get cancelled. Again, this one is the f of x. Then it is also written in the 1 into f of x. Then 1 plus delta into 1 minus nebula is equal to 1 into f of x. Then f of x will get cancelled. Therefore, 1 plus delta into 1 minus nebula is equal to 1. This is the proof. So next operator is E, and then next relation E is equal to e to the power hd is equivalent to again 1 plus delta. So whether D is differential operators of differential calculus, ये D differential operator है, differential calculus में बात use. So this proof of is A of f of x is equal to f of x plus h. So here we use Taylor's theorem. E of f of x is equal to, what is the Taylor's theorem? Taylor's theorem say f of x plus h into f dash of x divided by 1 factorial plus h square divided by 2 factorial into f double dash of x plus h cube divided by 3 factorial into f triple dash of x. This one is this denotes the third order derivative. This denotes second double dash and it denotes the second order derivative. So till this process continues and so on. Here we write again E of f of x is equal to f of x plus h into f dash of x. We write here f dash of x is equal to d of f of x. D and a differential coefficients plus h square divided by 2 factorial. It is f double dash of f of x, yani second order derivative, yani d square f of x plus h cube divided by 3 factorial. It is also written in the d cube f of x, and till this process continues. So E of f of x is equal to, we take f of x is a common, in bracket 1 plus h d plus h square by 2 factorial into d square plus h cube divided by 3 factorial into d cube plus h raised to 4 divided by 4 factorial into d raised to 4 plus and so on. So dear student, this is the series, exponential series. We write here e raised to x is equal to 1 plus x square by 2 factorial plus x cube by 3 factorial plus and so on. Then compare this e raised to x. Here we write instead of x here hd. That's why E of f of x is equal to f of x into e to the power hd. So f of x will get cancelled. Therefore, e is equal to e to the power hd. Then similarly we prove 1 plus delta. This is also equivalent to 1 plus delta. This is the sixth relations of delta, nebula and E. So next one is one more theorem. Prove that another one relation is prove that delta f of x into g of x. Just this is like to be u dot v, yani just d dx of u dot v. So here we write delta f of x dot g of x, delta f of x dot g of x is equal to f of x plus 1 into delta g of x plus g of x into delta f of x. So proof is very simple. So delta f of x into g of x is equal to f of, according to definition, f of x plus 1 into g of x plus 1. Here we use taking h is equal to 1. So this is f of x minus g of x. According to definition of delta, f of x is equal to f of x plus h minus f of x. Here we take h is equal to 1. So f of x plus 1 into g of x plus 1. So we add and subtract one more term, f of x plus 1 into g of x plus f of x plus 1 into g of x. Then we subtract this term and add these similar terms minus f of x into g of x. Then we take the common of this both the terms, f of x plus 1 then we write again g of x plus 1 minus g of x. Then these two terms we will get common in g of x. Therefore, f of x plus 1 minus f of x. So f of x plus 1, this is according to definition of delta f of x is equal to f of x plus 1 minus f of x. So we write here, this one is the delta g of x plus g of x into this is delta f of x. This is the forward difference operator, if product rule hai. And again second thing is division. We similarly prove the second rule is division rule, delta f of x divided by g of x. Just we write here g of x into delta f of x minus f of x into delta g of x divided by g of x into g of x plus 1. We prove this using previous results. So next one is fundamental theorem of difference calculus. So what is the fundamental theorem of difference calculus? The nth difference of a polynomial of degree n, fundamental theorem of the difference calculus. So the nth difference of a polynomial of degree n, nth difference of a polynomial of degree n is constant and higher order differences of 0. If ux is a polynomial, we take ux is a polynomial of degree n. Ux is a polynomial of degree n. Then we write here ux is equal to a0 x raised to n plus a1 x raised to n minus 1 plus a2 x raised to n minus 2 plus and so on plus dot 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 up to an. Here we provided that a0 is not equal to 0. Therefore, we write here del n ux, yani we take the nth difference of the given polynomial. This polynomial is the degree n, then nth difference is equal to, we put the directly result a0 n factorial h to the power n. This is constant term. But we take del n plus 1 of ux is equal to 0. Means according to the fundamental theorem of differential calculus, the nth difference of a polynomial of degree n, the nth difference of a polynomial of degree n is constant, but higher order difference means n plus 1, n plus 2, n plus 3 like this are equal to 0, are equal to 0. So then we again last point is factorial notation. Again write factorial notation. So what is the definition of factorial notation? X to the power n, this is equal to x, x minus h, x minus 2h, x minus 3h, and up to dot 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 x in bracket x minus n minus 1 into h. So E is called factorial notation. E is called factorial notation. If here h is equal to 1, we write again. If here h is equal to 1, then we write x to the power n, yani this factorial notation of n is equal to x in bracket x minus 1, x minus 2, x minus 3, and dot dot up to x in bracket x minus 1. So what is the factorial notation of, for example, we write factorial notation of 1, we will get x. Factorial notation of x to the power 2, this is equal to second order factorial notation, x in bracket x minus 1. Again x3, this is equal to x minus 1, x minus 2, and till this process continuous x4. Again we write here x minus 1, x minus 2, x minus 3, and so on. These are the factorial notations. So today here we stop.
Yeah.
Any questions to the students?
Hello.
Huh, sir. Hello.
Now the participants are requested to ask their questions, doubts to the Chavan sir. Now the session is open for questions and answers. Any questions from the participants? No one have a question. Okay, can we stop the session?
Okay, sir. Okay.
There is
Thank
no
you.
any question from the audience. Actually, Dr. S.B. Chavan sir have given one nice thought on the numerical analysis. Actually, sir have explained each and every aspect in the numerical analysis. From the beginning to the application, sir have given so many concepts in front of audience. Now I thankful to the chief organizer, Dr. Punjab Rao Chavan, principal of the college, convener Dr. S.B. Chavan sir, co-convener A.B. Chavan sir, chief organizing secretary. I am very much thankful for this nice event and giving me this opportunity. So thank you one and all. Can we stop, sir? Chavan sir?
Okay, sir. Thank you. Thank you very much.
Thank you, sir.
हा सर बंद करतो मी.
Oh, okay, sir. Okay, sir. Okay, sir.